If you thought that determining the heat released from a proposed hydrocarbon and air, hydrocarbon fuel and air combustion situation was tough, it's even a little tougher to determine the temperature at which that reaction will occur. And so this module addresses that situation, although the fundamental governing equation, the first law of thermodynamics, is still the starting point. A common objective is to try to figure out at what temperature will this flame occur, right? And so in other words, if you think as a mechanical engineer and you're trying to study cycles and the performance of cycles, you need to get a handle on what's TH. What is that high temperature heat reservoir operating at? So this is a way to get to that understanding or to estimate this computationally. And this is called the adiabatic flame temperature. A little more on what that means here in a second. As we start with a sketch, what does adiabatic flame? So flame temperature, you have a pretty good feel for. You know that you don't stick your hand in a flame because you know it's going to be hot and you know it's going to be a high temperature. It's just a question of how hot is it going to be. So here's our sketch. We're going to start with the first law of thermodynamics. And we'll start with a sketch to define what adiabatic flame temperature means. And so I've started with that same sketch, but I've made a point to crosshatch to show that the surface of this, the surface of this combustion chamber is fully insulated. Fully insulated. So there's no heat transfer across the system boundary. So this flame is sitting there burning, and what's going to happen is that, do you see that the combustion products, if there's no heat transfer to the surroundings, the temperature of the combustion products is going to be as hot as it possibly can be, right? So your common sense tells you that if there is heat transfer across this boundary, the combustion products would be at a lower temperature than if this were fully insulated. So that's the physical meaning of the adiabatic flame temperature, meaning that there's absolutely no heat transfer crossing the system boundary. And also, of course, for this combustion chamber, there's no output power as well. So we're going to rehash. And so we start right back with the fundamental of the first law of thermodynamics, recognizing that the whole left-hand side becomes zero. So we're going to say that there is no heat release from the combustion chamber to the surroundings. So that all of the heat that's released as a result of the chemical reaction, the combustion reaction, is contained within that combustion chamber. So this Q dot over N dot, that's going to be zero. We're fully insulated. Also, no, we're not lifting a weight, no shaft coming out at a known torque and speed. So the right-hand side becomes zero. And so the idea is this is a balancing act, right? So since the left-hand side equals zero, the sum of the enthalpy terms of the products must exactly equal the enthalpy terms of the reactants. Products, that's the exhaust gas. Reactants, that's the fuel in the air that's coming in. So it's a balancing act. So the adiabatic flame temperature will be the temperature at which the enthalpies balance one another between what's going in and what's going out. And so do you see then that the adiabatic flame temperature kind of represents really the maximum possible TH that can be achieved by your proposed combustion process. And so what's your proposed combustion process? Well, you're going to propose that you have C sub M, H sub N, and you're going to propose that you have a certain amount of excess air. It might be 0 or stoichiometric, or it might be 10% excess air. It might be 100% excess air. And does your common sense tell you that as you increase the percent excess air, your adiabatic flame temperature will be a lower number, because all you're doing is heating up excess air in the process. So that's a common sense thing to think about, that as excess air is increased in the combustion process, the adiabatic flame temperature decreases. Okay, so that can help you conceivably in solving engineering and homework problems. Let me try to explain to you how come this is even more complex than determining the heat released from a proposed combustion process. Okay, solving for the adiabatic flame temperature. So you've got one equation, okay? It's got to equal to 0, so that looks pretty good. You do remember that each one of these blocks of terms is complex, don't you? You remember that each block is complex. Another thing to remember is that these delta H blocks coming in, delta H, the temperature of what's coming in relative to the reference. Exiting, the temperature, the enthalpy relative to a reference temperature. So do you see that these delta H terms, and in particular this one, do you see that this delta H term depends on the temperature of the exhaust? This delta H term depends only on the temperature of the air and fuel going in. But this is tough, right? Because you don't know what you're trying to find, the exiting temperature for the adiabatic process. And so this block term here depends on temperature, but you don't know it. And so here's the, pardon me. Here's the solution technique down here. You have to guess the exit temperature of the products. You have to guess the temperature and solve for the heat released. If it's non-zero, you got to keep guessing the temperature. Okay. And so you have to recognize that this Q bar term has got to equal 0. So I'm sort of, there's the Q bar term there. It's got to equal 0. So you've got to guess the temperature until you guess correctly. Now, so in the real world, what you do is your first guess needs to be a high number. You have to guess way too high. And then you guess, and you're going to get a value for Q. And you guess too low, and you get another value for Q. One or the other of those is going to be a negative number, and one will be a positive number. And so then you keep guessing in between those brackets until finally you bracket in and you've guessed the correct temperature. Thus, my automated Excel tool, when I've been trying to calculate the adiabatic flame temperature, imagine what you'd have to do if you're working this on pencil and paper and having to do and calculate this block of terms over and over and over again. I think you're going to find that all these other 3 terms are static. You only have to calculate those once. But this term, you've got to calculate over and over and over again. It can be very tiring if you're doing it by hand. So as a reminder, I want to show you how to download my combustion reaction calculator tool. It's a generic tool, okay? But also its purpose is not to determine the adiabatic flame temperature. Its purpose is to determine the heat release. But do you see that in my world, if I can use this tool to determine the heat release, I can guess a high temperature, I can guess, and I'll write down a numerical result. I'll guess a low temperature, I'll write down a numerical result, and then I'll start honing in on my guessed temperature until I get to a Q value of 0. Let me get out of PowerPoint. Okay, here's Jay's toolbox, jaystoolbox.vt.domains. I'm going to drop down my toolbox menu and go to Excel Docs, XLS Docs, and pick Thermal Systems. It's thinking. And I'm going to scroll down. And depending on whether your problem is in English or SI units, you'll download one or the other of these Excel files. You possess that Excel file. There's no passwords or anything. You save it to your computer and use it as if it's your own. You don't want to turn in my work and represent it as your own, but you could use it as a tool to supplement and check on your own work as you go along. Let's go back to PowerPoint. Okay, so that's the way you can get to my automated tool that might help you check your work. Here's a screenshot of my using that tool a couple of times to hone in on the adiabatic flame temperature. In other words, for this sketch, for this combustion chamber, where Q dot in is 0, W dot out is 0, I'm trying to figure out the temperature of the combustion products, the adiabatic flame temperature. Well, here I've guessed 2060. That's a low guess. 2060 degrees R for this particular problem I was working on. And I go through all the numbers and I get a Q bar over N, in other words, BTUs per pound mole of negative 5,480. Now that's almost zero. It turns out that's almost zero, but it's negative 5,480. Do you remember in a previous module, I calculated the heat release and it was like 320,000 BTUs per pound mole. So 5,000 is a lot lower than that. So I'm getting close to a result guessing 2060. I guessed a higher result, 2100 degrees R. The Excel tool goes and looks up all the numbers for me. It does that accounting problem, and the heat released when you guess 2100 degrees R for T sub P, you get plus 6493. So my practical conclusion using this tool for adiabatic flame temperature is that that temperature is going to be somewhere between 2060 and 2100 degrees R. Look, for engineering purposes, that's going to be close enough. Now, you could even sort of linearly interpolate, since you have these values and these values, you could do a linear interpolation to get a number between 2060 and 2100. But look, you ought to be pretty proud of getting this far. And so I hope that I've demonstrated how you can use my heat release generic tool to look for the place where the Q value, Q over N, Q bar, okay, switches sign, S-I-G-N, and that tells you that you have bracketed, and here it is, this T sub P in the sketch, this T sub P, that would be a number, let's say 20, I don't know, 2080. Let's say we did the linear interpolation and got 2080. That's what TP would be. So you're going in at the given conditions, and you're solving for the adiabatic flame temperature, and TP would be 2080 degrees R. So in the real world, that would give you an estimate for T sub H, and that can help you in your engineering analysis determining, the maximum possible thermal efficiency of a proposed cycle, and can really help you out. Can also help when you're designing equipment. It helps you design for a certain maximum temperature in the combustion chamber. So you can see a lot of practical applications about determining the adiabatic flame temperature. So there is a need for this. We're not just being mean and deciding to torture you with computations. So I hope that my automated tool might help you as you go through these very complex calculations. Okay, so what we just covered was how to determine the adiabatic flame temperature for a combustion situation. It is a complex first law analysis for steady state, steady flow open systems with no work involved, fully insulated reaction. I do hope you see that this type of question could not possibly be given on a test or exam because it can take a long, long time to get to a numerical result. Certainly, on a test or an exam, understanding the meaning of the adiabatic flame temperature could be covered, right? Because step one, it's based on the first law of thermodynamics and energy balance. So that could be good to know. Be good to know what's behind the adiabatic flame temperature. But to get to a numerical result, you've got to keep guessing the product's temperature and keep guessing until you find where there is no heat transfer from the combustion reaction to the surroundings. So that's the key. I hope I've illustrated to you in Chapter 13 how determining the heat released as in combustion, determining the flame temperature for adiabatic combustion, all of those both fully depend on a restatement of the first law of thermodynamics. When you don't know where to start, you don't know what to do, let the first law of thermodynamics become your friend. Write down the first law, and generally, that's going to help you get to an approach.